So I'd like to revisit the question that I asked you, Erwin, about blackheart and pomegranates. And so it's my understanding that it's caused by the fungus alternaria. And so would we be able to put a VOC on a Tomra sorting line to be able to detect at full speed of sorting the blackheart and pomegranates?
Let's get some plumbing and find out. We've done some, actually with the nursery ornamental work where we're looking at, kind of screening, again, a lot of concepts we thought about for VOC sensing, we're using it as kind of the first pass to see if there's something within, a situation where you need to go in and take a closer look. So we've done work where there was a soil pathogen in nursery ornamentals. And we collected water runoff from when the nursery was watering them. And we saw direct signals of when that pathogen was present. We go back through and do a little bit more testing. So, again, it depends on the case. It depends on the presentation of the fungus. If a VOC sensor could be used, I'm curious to more. I don't know too much about it, so I don't know if it's internal or external. But the technologies are changing too, where we're trying to get faster, high throughput measurements of VOCs to be able to do that. I don't think we're quite there today, but I think certainly the fundamental research of just being able to see if it's possible to detect it is present already.
Just a quick follow-up. So at the speed at which one of your packing lines run, would a volatile detection be possible per piece of fruit?
Good question. We have to research it. One of the things I was thinking about during his presentation is that maybe you could use it in a different way as well, or at least where you can at least evaluate the batch. You have this lag time. If you could sense it, let's say right after harvest or during harvest, and then it gives you tools to be able to handle that product better during the processing time. Maybe that's a stepping stone into it.
Yeah.
To add to that, I was very skeptical, and I invited Mitch, and I was transparent at the beginning, telling him that I was skeptical in this field, especially because we've had such, I don't want to say bad, but some negative experience with electrical osmosis. But there's a difference, and one thing that I've been learning from Mitch and basically submitting this proposal together is that we can be very targeted now. And more specifically, these techniques have changed in the past since you started working on this, basically in the past 10 years. It's almost in parallel to the cell phone. And David Slaughter did that analogy that it's 1,000,000 times more powerful than the first person that took the first computer that took the first person to the moon. And what they're exploring right now, adding either some sort of sensors or this in a cell phone or whatever, there is potential, yes. For the pressure in a company like Tomra is that we are asking them to never slow down. And that's the nature of humans, especially in North America. If we look at the difference between generating sorting technology for like the Japanese market, they can afford to sort 40 items per hour. They don't care. You can get a melon in Japan that is worth $200, $400 basically as a gift. So they want to have a perfect melon. But that's not the case here in the US. It's a different market. So the bottleneck for us is, again, throughput, 400 items per second. And that's where it's tough. But to add to what Roberto was saying, this could be either explored as more like a batch level, or we don't know. See, we can't answer that question right now. And that's the part of the conversations that we're having right now. We can explore this further now that we are specifically targeting those compounds of interest. We can oversimplify everything. And that's what we're basically doing with Mitch's team. We're exploring into building a simple sensor that we can give a shipper where they can collect volatiles from the whole container, and they're going to tell us, yes, there is this insect present in there. So that's huge. It's huge for phytosanitary reasons, quarantine reasons, for many reasons. So now we have the ability of doing that. But I think my personal opinion, what I've seen is that this has changed in the past five years or so. Even the techniques that what Roberto was saying, the pulse LED, for example. Why are they using pulse LEDs? It's a way of, it's another sort of illumination. The pulse LEDs allow for energy conservation, heat, mass, less heat, and therefore, you can make things much more cost effective too with LEDs, many aspects. And it's like the only thing an LED or a pulse LED is doing is just the same illumination, only that it's turning on and off at a very rapid rate. But we're still using the same cameras and everything for that purpose. Another technique that we didn't mention much right now that could potentially be feasible for damaging, so they're not even visually evident, is your laser. Laser is a little bit different. Imagine that you have a pointer, and if you aim that pointer at a pomegranate that has a different texture because it's degrading of some sort, then that laser is going to disperse differently. It's going to have a different shape. It's not going to reflect the same way. So now with laser, we have a potential of doing that even further. And now another layer. Talma now is talking about multi-sensor technologies, where we have cameras, lasers, X-rays, and then we can go through different steps to be able to sort this. And I do not see this as impossible with VOCs. So then we can have different layers of this. That's where we're going, and that's where the industry is aiming. So I do see it as a potential. Is it going to happen in the next 10 years? I don't know, but let's find out.
Would you expand a little bit on laser, like how it works? Is it like use any specific wavelength or anything? And how it could be useful in like a post-harvest quality evaluation?
I can expand a little bit. Laser is basically a monochromatic, so it's non-specific to the wavelength, and it's just basically a shape distinction. I should have showed those pictures, but it could be a good reflection of textural changes. A firmer product is going to reflect that laser. The laser is going to bounce much more than if it's not. It's going to dissipate within this less firm product. So it's a combination of the laser and some image analysis where you could do some textural analysis of firmness. That's when firmness comes into play, for example. And that's where the laser is. It's defects, surface defects, and so on. That's how you do it. But it's not just one laser. In their case, it's an array of lasers that are operating that information. Would you like to add more?
In addition to that, firmness, we've done various work on that, and our spectroscopy itself, it's got the ability to measure water content on the surface. So that has given us as well some results in the past. But it depends on the product itself. So maybe more specifically, we can talk offline on the details. But there are some possibilities there on the firmness.
I had a question actually for Galen. For your non-destructive bricks device, I think specifically like for the mango one, do you have problems that occur when you're having non-uniform sugar distribution throughout the fruit? Like one side having more bricks compared to the other, and how do you deal with that?
Yeah, absolutely. So, and that's one of the big hurdles with the portable devices is when you're dealing with fruit that aren't completely homogeneous. So when you've got heterogeneity and distribution of your biochemical things like sugar or starches or oils or whatever it may be, you have to be able to combat that by what we typically do is encourage multiple scans per fruit in multiple locations. So for avocado with dry matter, that's a notoriously heterogeneous fruit. So you could sample flesh from one part of the avocado from like from the neck, and then another part from the bottom near the pit, and they would be 14% or more different in dry matter if you measure them analytically. So the way we get around that is you measure multiple spots, and then you take and then the device itself takes the average. So we have settings built into the device to allow you to customize how many sides of the fruit, how many scans per side of the fruit. So with melon, actually, we get our best results when we do, I mean, with any fruit, really, you'll get your best results if you take, 6 or more scans at varying locations on the fruit. And so with mango, what we do is 2 sides. So one on each cheek of the mango, and then average those. And the instrument will actually also automatically take 3 pulses. It's like 3 scans, and those allow for even more increased accuracy. So you're basically averaging almost a total of 6 scans on one fruit, but it's still only taking you, a few seconds. But that's how you would deal with the heterogeneity issue with the distribution of bricks and dry matter.
No, a question from Galen. For avocados or for the product, what type of calibration your equipment require? Because most of the time you work with different countries, source, currently Colombia, Mexico, Chile, Peru. So do the equipment require constant calibration for each country? No.
So there's a couple of different things to speak on when you're talking about regionality and its effects on developing these models. And one of them is that we do our best, and as I mentioned with our collaborator kind of initiative, is that we do our best to incorporate as many regions as possible into the model itself, so that you don't have to do these kinds of extra calibrations. However, when that's not always possible, what regionality typically presents itself as a bias in the predictions. So what you may see is, for instance, you're measuring, you're using the instrument in let's say, trying to think of a region we don't have a lot of data from, South Africa. Say you're doing South African avocados, and you're taking all your scans, and the instrument's giving you a certain value, a predictive value for all those different avocados. And then you just, as a check, you want to actually test them analytically and see how close the device is comparing to your analytical method. And you realize, you look at the data, you see what typically you'll see if the model doesn't have a lot of data from that region, you'll see that it's going to be consistently over or under predicting. So it's a bias in your prediction. And so in that case, we have a setting where you may have to, and it's not that common, but you may have to go in and adjust the what we call, the bias of the instrument, in order to take all those predictions and bring them down by 3% or increase them by 2% or whatever it is, to get them to a more adjust so that they match up with what your current analytical methodology is. And so that does also apply to things beyond regionality, like cultivar. Sometimes it presents itself as a bias if we don't have a certain cultivar, like a tropical green skin avocado in the model that you are looking at. But yeah, it's so we try to make sure that we don't have to have that much calibration to the instrument, but in some cases the calibration is required, where basically you just do what I laid out there. You scan 10 fruit with the instrument, measure them in the oven, and then compare the 2 values and see what the difference is, and then input that value into the device.
Thank you.
To add, sorry, just to add to to that. That's why the mango calibration models are so successful for Felix. One of the reasons is because Dr. Wallace is his name, huh, Galen?
Yep.
Yeah, Dr. Wallace in Australia has done an incredible job over many, many years, like Galen mentioned, up to, I think it's 8 to 10 years, like you mentioned, Galen. And they've even studied the temporal effect, the geographical effect, and they have correction factors for all of it. See my point? That's why it's so successful for the Australian model. That said, it doesn't mean that immediately it will be successful for any other model that you're trying to build. But as you offer more information to that model, that's when your accuracy rates tend to increase. So yes, these are retrained every time, and you get an increase and a reduction in that bias, like Galen is saying, to a point where after several years, you could definitely use this tool as a replacement to any destructive measurement. But it does require a calibration process. That's the nature of this pieces of equipment.
We also can understand why Australia can be involved, because, I don't know, correct me if I'm wrong, Galen, but I heard they ripen a lot. They have a good culture ripening mangoes, like in other countries, like in Europe, for example, UK, Netherlands, versus here, that also much with your comment about people who want to eat mangoes here, because people started to buy portions of the mango and eat it in a week. So there are also like, maybe that's the reason with Australia, because they ripen a lot better.
Well, and Dr. Walls, he's one of the creators of this piece of equipment. You know, it ties well. Having an expert, a renowned expert in this field, it ties well with, you know, the success of those equipments. You have the know-how, you know. What was the predecessor of Felix? It was a different brand, Galen. Do you recall? That's the one that...
Yeah, it was called the Nirvana, I believe.
The Nirvana, yes.
Yes.
And all of us that started working in near infrared, you know, were familiarized with the Nirvana. Felix's version 2.0 improved the Nirvana. And who's the Nirvana guy? Dr. Walls from Australia. So that's why it's successful. Just a little bit of history to that. Sorry.
As a follow-up for the same question, so I wanted to ask, imagine working with the same crop, but do we need to do the calibration each season because of the changing environmental factors as well?
I will share a very interesting article that Dr. Walls wrote regarding that topic. Yes, but as you add more and more seasons, and correct me if I'm wrong, Galen, that accuracy rate tends to reduce to a point where it's undistinguishable. See my point? So yes, it depends on the application. It is ideal for you to generate models not in one season. The robustness of the model increases as you add more and more seasons. Dr. Walsh has done a very good job because they have so many years of data, especially with mangoes. Not only that, also temperature compensations, everything, you know, that is very, very enlightening. So I'll share that document with you because it's a very good read and it addresses your question directly.
Perfect, thank you. And yeah, go ahead.
Just to add on that is yeah, from what we can see with the models that we have had since the kind of creation of this technology, and its deployment in this industry is there almost seems to be it's not quite cyclical, but I want to say a cyclical nature to seasons. And so at a certain point, as everyone said, and usually it's somewhere between 3 to 5 seasons, that you no longer have to keep adding new seasons worth of data. And because the conditions tend to, all repeat themselves to a certain extent. And so you get all that variation already in the model. Now where that is going to probably, be less and less likely is now that with climate change, we're probably going to see that cyclical nature a little bit, destroyed in some sense. So we're going to have to probably, compensate with that by adding in data every year as a fail-safe. And it is, like I said, it's never a completely finished product. It is in the sense that you can buy one and you can own one, but it's not in the sense that these models can always use a refreshed data set, new data, new regions, new variety within the data.
Okay, so basically you're saying that 4 to 5 seasons should be enough, right?
Yeah, and we even have success with less, like seasons. So it depends on the commodity and the region that it's being used and what's in the data set. So, like if you, for instance, created your own model for your specific cultivar of, let's say, apples. Say you're working with Cosmic Crisp and you're in Washington, and you only are interested in Cosmic Crisp. Then, if you're only measuring in a certain region, your data set, over 2 seasons, after that, the 3rd season, it probably is going to predict pretty well. But then when you go to extrapolate that to, I want to measure all apple varieties all over the world, that's when you start to run into more and more issues where you need more seasonal data. So it really depends on the specificity of the model, but with these general models that we're creating that are supposed to be more geared toward a global audience, then yes, we try to make sure that we're incorporating as many seasons as we can. We don't really stop ourselves from adding more, but yeah, generally speaking, the research shows between 3 to 5.
And it's natural because look at the talk that Mitch offered today of how sorghum communicates with tobacco. You said as soon as there's something, whatever, an insect, and then they evolve. This is things that we're learning. That's why this near infrared models also evolved, because like Galen very wisely mentioned, climate change. Now plants are creating mechanisms that they change, the fruits change their structure, the biochemistry, and that's what we're measuring basically. And as we change, the weather changes and so on, the plants are going to adapt. And we're learning more of that I learned that from your study today. So yeah, it's the nature of these models.
I was going to say, we see the same thing in VOC sensing too, Galen, where, you need the additional seasonal, you need all the biological noise to go into it, right? Because that just improves your accuracy in the long run. So similar to us, multiple seasons, multiple varieties, all of that really benefits an overall global model.
That's when AI comes into play, okay? That's where, I jokingly say AI is not the miracle, but it does, because it's an eye-opener for when you add more. Now we have the capacity of zooming in and trying to build models that are more robust and are more accurate because we have newer methods like AI, that are building that we did not have. Roberto mentioned that now some of their equipment use AI, others use traditional chemometric measurements to calibrate. As you build those models of AI, then it's almost nearly going to be perfect, to a point, where you get.
So you guys mentioned variety, so we can have one model for several varieties. We don't need to have separate models.
I'll let Galen speak on his technology first.
Yeah, so with NIR, it really depends. We've had luck combining data sets with like mango. So mango is a great example because in the mango models, there are, I think, 7 or 8 different cultivars in one model, and you don't have to switch the models between the cultivars. Kiwi fruit, however, between the difference between a gold kiwi fruit and a Hayward and a red are different enough that it warrants, accuracy-wise, it warrants having different models for each one. So it really depends on how accurate you need it to be. Avocado, for instance, when you're going from a Hass to a Pinkerton or a Fuerte, a green skin avocado, sometimes, it works to be able to, have them all in one model. Sometimes if you really need that increased accuracy, it's going to be better to break them apart. So it really depends on what your threshold is for accuracy. In general, it's always going to be more accurate to split them up into separate models. because you're just making it more specific, each model more specific. But otherwise, for realistic purposes, it's not a great presentation to customers to show them a device and say, okay, here you have to choose from 100 different models. Every time you go to scan something, you got to choose the right variety. So it's a balancing act, but it's like I said, it's gonna give you the best accuracy to separate them out, but sometimes it's not worth that little bit of extra accuracy.
Thank you.
I have the same findings. I feel like we're selling a bunch of lawyers up here always. It depends, but it depends.
It depends.
It depends. And I think with the strawberry case too, those were all the same species. And so even though there are different varieties, we are still picking up, like it shouldn't matter if I'm a redhead or brunette, if I'm doing some kind of clinical diagnostic, I should get the same result out, right? But in our case for citrus, there was difference by what we would call variety because, in citrus, there's basically 3 species that are making up all the different types of citrus that we eat. So there's more biochemical complexity there that we have to account for. So it depends. Very unsatisfying answer.
No, it's the safest answer. That's what we have to answer all the time. It depends.
So just be reading one of the questions from our online participants. So Maria is asking, I guess this is for Mitch, how sensitive are VOC sensors, and can they react with similar compounds and give us non-accurate response? Any ideas to prevent that?
It's a really good question. So in terms of the just absolute technology to measure compounds, it depends. Because what we need to do is actually to measure these compounds, they have to get ionized. And there's many different ways you can ionize them, lots of safe ways. But every chemical has a difference in its stability once it's ionized. It wants to react really quickly. Some can survive it longer than others. So that plays into fact about how well each compound has for its detection capabilities. So it depends on what chemicals we need to measure for whatever the application may be. Most organic compounds that we see are definitely stable enough for the measurements we're making, but we see better sensitivity for some than others, and that's usually related to how well they ionize. The other thing to keep in mind, though, is that it also depends on the rate that these compounds get produced by the produce. Some of them produce them in much higher rates, and therefore there's a lot more of them available to measure, and others are slower in that process. So you need to maybe capture more of that sample to have enough of it to get to a detectable level. So, in general, a lot of the technologies we see now are definitely within the low part per billion to high part per trillion detection levels, I would say, generally speaking. And then you have other technologies like the pre-concentrators I mentioned to augment that and increase it to part per, much lower part per trillion levels. So, and there's a wide range here depending on the detector and the application.
All right, so I guess this is partially answered before. This is for Galen, but anybody can answer this. What are the main challenges or limitations that you have experienced when developing a new model?
The biggest challenge is when you're building a new model is, it's not in the mathematics. It's not in any of the actual, chemometric stage or anything like that. It's actually in the data collection process. Inconsistencies across, we don't have a world government regulating how everyone's testing their produce. Everyone tests it in a different way, and sometimes they're heavily regulated on how they do it. Sometimes they're not regulated at all, and they're doing it voluntarily. And they're all using different technologies to measure it. They all think their current technology is 100% accurate, even though they're using a pocket Atago refractometer and thinking that's that is the true 100% truth. And even those have limitations. So it's really the biggest challenge is trying to ensure that all the data we're going to collect is is good data, is high quality data, that is going to actually improve the model and not confound it with error from the technology being used to collect that data or the user methodology. So trying to find a uniform way to collect data, when you're combining, avocado is a good example. In Mexico, half the time they're using ovens, half the time they're using microwaves. Some people are sampling the entirety of the avocado flesh. Some people are only sampling a small ring around the entire thing. Some people are doing 5 grams. Some people are doing 10 grams. And funnily enough, just evaporating water out of something is one of the hardest things to do, because water likes to be bound at a certain level, and so it doesn't like to go away without you cranking the heat and then accidentally combusting other things and losing a lot of volatiles that are then mistaken as weight lost by water. So that's the biggest challenge with building chemometric models, is making sure your data input is of high quality and consistent.
There's a party somewhere.
This question is for Galen. So if one works with multiple fruits, for example, would you suggest them to buy the number 4? I don't remember the name. Because there was one for kiwi, one for mango, I don't remember the other one. There was melon, and then there was one that has no specific name. So would you suggest them to buy that one if they are working with multiple produce, and then make a model for each produce in there? I don't know. And which one is more expensive? Will it be more expensive than the other one? I don't know.
So for specifics about applications, which meter should I get? I would highly recommend that you just reach out to me directly, and we can discuss your application more offline. So that, but in general, as I mentioned, we have these commodity specific meters. If your commodity that you're working with is not represented by one of those, or any of the ones that we're working on right now in development, then you would want to create your own model. If we're not going to be planning on doing it on our own, because we have limited resources, we can't. We would love to build a model for every possible commodity out there. That would take a whole entire country's worth of people operating around the clock to get that done. So, I recommend getting in touch with me, and we can talk about your specific application. But in general, if it's not represented by something we're selling, if your commodity is not, then you'd want the F750, which is the open-ended kind of research unit. That's the one that all the breeders and high throughput phenotyping people use, because they're always looking at traits that we not necessarily aren't concerned about in looking at harvest maturity or things like that. So that is kind of the path if you would want to go, if we don't have that commodity available to you in a 751.
Thank you. And the question is for Mitch. So for the VOC sensors you are making, are they for traceable amounts, or how high can they go? And do they have enough memory for a library, or just they are geared for just one compound?
Yeah, these are good questions. I mean, there's fantastic national databases for mass spec VOC data where NIST does, they collect hundreds of thousands of measurements, and when I measure something on my mass spectrometer, I can go compare to that database and get more information. But that's commercial devices. For our custom devices, that would be, quite an endeavor to build a giant library for all the chemicals there. So we really focus on the chemicals that are important for the application. So the 2 most mature versions of our tech that we have today are working towards that breath test for COVID. And we actually also are with the North American natural gas utility companies. Natural gas has no smell. They add in mercaptans, which are volatile compounds, to odorize it. And so we're actually have 10 prototypes that we're delivering to agencies there for them to measure. Those happen to be in the part per million range, so it's actually pretty easy. For the breath work, we're still determining exactly what compounds. Turns out that the variance threw quite a curveball there, actually, in terms of the clinical presentation of them are so different that the breath biomarkers are now pretty different as well. So we're determining the exact ones that we need for those tests. But yeah, and that's why we incorporate a lot of that pre-concentration so that chemicals that exist in your breath in part per trillion, we're actually kind of concentrating them up to a detectable level for the device. So, yeah, exactly. So that's one approach to compensate for something that might be in a really low abundance. Yeah.
Yeah, I have a question to the panelists. Like, if you were asked to choose a gold standard method for measuring, let's say, soluble solid or dry matter, which one you pick?
Could you repeat the question, please?
Like, if I asked you method for like a standard method, right, for measuring the bricks, which is soluble solid or dry matter, like which methods, like from your experience, you can suggest us?
So both dry matter and bricks, in this case soluble solids, can be fairly well calibrated with near-infrared spectroscopy. For example, the Felix or near-infrared imaging, like what is done online, for example. Both need different calibration methods, and I guess it depends on the crop, what you're trying to measure. For example, in some instances, dry matter might not be a good indicator of maturity for certain crops, but it's for others. But near-infrared spectroscopy would be my suggestion.
What's the gold standard, though?
Oh,
The gold
the
standard.
gold standard, the comparison, like the reference.
Yeah,
the reference
for bricks or.
The reference for bricks is a refractometer, basically, which is an indirect measurement of soluble solids. It's not necessarily just sugars. And dry matter is just drying, basically a ratio between mass and water. So that's why when Galen is mentioning how you calibrate the dry matter prediction models, is they're drying it in the microwave. He mentioned it's kind of like briefly.
Is there an industry accepted standard?
The oven method is the most accepted, and titration too for dry matter. Those are the two.
Yeah, I'm also wondering, like, if we measure something with this device, like, can we use it for publication?
Sorry?
So if we like measure, let's say, soluble solid or dry matter with Felix, we can publish this. The data will be accepted to the peer review. I don't know, like, will we face any questions like how we are accurate about the data that we get?
Oh, that's our role. I have several articles, for example, that include Felix and other companies too. There is another company called Zio, for example, that produces small-scale refractometers, where we have evaluate their performance very objectively with different crops and so on, and we develop the calibration algorithms, and it's very broadly accepted. Yes. Oh, yeah. Yeah, last question. It's already 10 minutes after 5 and they're kicking us out.
Yeah, I promise this is the last one, I guess. So you were discussing about the depth of penetration of infrared, that it doesn't work on some of the crops like melon and watermelon, but based on what Galen was suggesting, seems like there is some hope. I actually talked to you last time about this, that our company is interested to find a way to measure grapes for watermelon when the breeder walks in the field and she wants to know the stage of maturity. So is there a way to do that?
Well, take my suggestion that the penetration is the only factor. As Galen has mentioned, you can have some sampling protocols that could potentially reflect this much more accurately. If we look at just the physics of light penetrates in near infrared a maximum of, and I'm exaggerating, 3 millimeters. In other words, light interacts with those cells that are within 3 millimeters. So it is expected that a melon that has a thicker skin in comparison to something like a cherry, that the accuracy of the sugar levels is reduced. But then, like Galen is suggesting, there's protocols where you could potentially sample the watermelon in multiple regions and potentially even remove a phase, for example, that becomes a little bit more destructive, but you could start assessing it in that way. But we also need to consider what you're measuring for maturity. For example, watermelons. Watermelons are more successfully, the maturity of a watermelon is, in many instances, is not related to its sugar level, but its acoustic properties. That's what I was saying. That's a completely different animal. See my point? That's a different approach completely. The calibration procedure and everything is very similar, but there's in many instances and in many crops where sugar levels is not going to be a good reflector of maturity. So again, back to Mitch's position, it depends. It depends on the application. And if you're interested in exploring that even further, that's what Galen is offering, to have either a direct conversation with you. They have models already in-house. They can test this too before you even potentially commit. It's not a sales pitch, but you could work with them to be able to evaluate if their models are feasible for your specific application.
Thank you.
And I think for the sake of time, it's already 10 minutes after 5. We need to finish. Thanks a lot for your time. I don't know if we have any final remarks from Roberto or Mitch. If not, thanks, and we will see you tomorrow.
Thank you all.
Thank you.
Thank you, everyone.
Thanks, Galen.
Thank you.
We'll see you
I'll
around.
see you later. Yeah.
Thanks. Bye-bye.
Bye.